This is looking at two approaches. One is where you've got a fixed pump speed and you get the part load conditioned by throttling. So this gives you a different profile than when you use speed variation. So to get these different points, you can either do it by throttling, in other words, your system curve comes up through those points, or you can do it by reducing the speed. And this is the approach that they've taken in Europe. So there's a difference between throttling and variable speed. The product approach only looks at the pump. It doesn't look at, or the motor as an individual component. So this is a pump. This is an extended product where you've got a load profile and a reference control curve to determine where the pumps will operate. So load profiles and reference curves come from the industry and in a cooperation with information that's given by the client. And it applies to closed loop systems or open loop systems and constant flow systems or variable flow systems. All of these applications are covered by this European approach, the extended product approach that they use in Europe. And this is the plan of implementation of these various legislation effects in the pump industry. And you can see that this started back in 2008, but was actually introduced as legislation in 2011, 2012, which is where it's been operating in Europe. So more than 12 years. And the extended product approach is where we look at the supply, the electric motor and the pump as a combination of products, where we're looking at a pump which has got a particular MEI and a motor that's got a particular IEX, which is the efficiency of the drive motor. The extended product approach is all of those combined together, and we measure at that with an EEI, which is for a pump, motor, drive package. This is just a very simple load profile for a closed loop system, and it tells us that it operates at 100% flow rate at only 6% of the time, 75% flow rate at 15% of the time, 50% flow rate 35% of the time, 25% flow rate at 44% of the time. And that shows you the various operating points. Now, if we do that with a fixed speed motor, we can only get those operating points by throttling. So what we're doing is this, that's the open valve curve, and that's the duty point with the discharge valve fully open. As we want to reduce the flow, we close the valve and we induce a different system resistance curve, and that gives us a different power demand, but not significantly lower than the original full load power demand. As we throttle further, we can see that our power doesn't diminish very significantly. If we look at the variable speed pump, we've got the same operating point for L1, but as we reduce the speed, our efficiency does not change significantly. So we get a much lower power draw for these other 3 points on the duty cycle. So this is the argument or the discussion that's going on in the industry. Where are the energy savings comparing throttling to variable speed? And you can make your own decision about which of those methods you're going to use. Here's a more complicated load profile, and you can see there's a much greater variation in demand. And you can look then at the system curves, and you can see that for those variations, variable speed is a much better way to go. Okay, with less nasty effects that you're going to get on the pump side if you've got a fixed speed. And again, you've got the various approaches. This is for throttling control. And then finally, we're going to look at the various components of the extended product approach. And this whole thing is the subject of investigation. We're not just looking at the pump. We're not just looking at the motor. We're not just looking at the drive. We're looking at the whole thing as an extended product approach. Okay. So we choose the pump operating at the best efficiency point if we can, which means that the pump efficiency is the hydraulic output compared to the shaft input. And the shaft input comes from the motor. So if you've got a fixed coupling, whatever the motor puts into the shaft is the drive power, and this is the hydraulic power, and the pump efficiency is the hydraulic power divided by the power from the shaft of the electric motor, assuming that the coupling losses are zero, basically. Okay. But we've then got to take into account that there will be a drive efficiency factor. If you've got star delta starters or normal starting devices, generally speaking, that the power going into that machine is very similar to the power that comes out. But as soon as you go to a variable frequency drive, the further away you move from 50 cycles, the more losses you're likely to have in the drive itself. So the extended product approach gives you the opportunity to build in that inefficiency factor from the variable frequency drive. So when you're looking at, do we have variable frequency drive or don't we have variable frequency drive, we need to understand a lot more about the system that the pump is operating in. For example, if we have a system where the pump is operating against a high static head, then generally speaking, throttling is a more efficient way of controlling the flow. But if you've got one that's got zero static, then variable frequency drive is a better way of controlling flow. And you'll find that in the HVAC industry, that variable frequency drive is very common for controlling variation of flow rate.